Hi, I'm Xizhi from Drexel University. This talk is about the paper Strategyproof Scheduling with Predictions. This is a joint work with Balkanski and my advisor, Vasilis Gkatzelis. So in this work, we're focusing on the tension between algorithms with worst-case guarantees and machine learning-based heuristics. On one side, the algorithms with worst-case performance framework offers really robust worst-case guarantees. However, these guarantees are often defined by a single worst instance, and sometimes they could be overly pessimistic and does not capture what is actually happening in practice. On the other side, we have these machine learning-based heuristics, which works very well in practice, but most of them do not admit any non-trivial worst-case guarantees. There might be instances that really breaks them. This recent line of work called Learning Augmented Algorithm or Algorithm Design with Predictions aims to resolve this tension by designing algorithms augmented with machine learning predictions or advice. Ideally, this algorithm aims to achieve really good, much better performance when the given predictions are correct and still maintaining the worst case guarantee when the predictions are arbitrarily wrong. So just to provide some extra background on the algorithm design with prediction framework, there has been more than 120 papers published on this with this framework in the past 4 years, and you can see the link I provided for the full list and check out other works. But in general, the framework focusing on algorithms that are augmented with predictions or advice about the instance. And there's no assumption in regarding how the instance or the input is generated. And the goal is to achieve optimal or near optimal performance when the prediction is correct, while still maintaining the best existing worst case guarantees. The two metrics used in this framework are called consistency and robustness, where consistency is the worst case competitive ratio given a correct prediction, and robustness is the worst case competitive ratio overall. So it's the standard notion of the worst case guarantee. And we're going to revisit the consistency and the robustness notion in the context of scheduling paper again. So don't worry if this is too abstract or too vague. Now let's take a look at the problem itself. Consider this very simple scenario with only one job and two machines. And machine one takes an hour to run the job, and machine two takes 3 hours to run the job. And of course, we wanted to assign the job to the machine one because it's more efficient. Now, unlike the algorithm settings, in here, we actually assume each of the machine is controlled by a self-interest agent. So the immediate consequence of that is we need to pay each of the machine or the agent for the job that they run. We need to compensate them. And for example, in this case, if we were to allocate the job to the first machine, we need to pay her at least a value of 1 in order to cover the costs that she needs to run the job. And if we pay her more, she's going to get happier. So the utility of the agent is defined to be the compensation they receive minus the processing time. And agent, whenever they can, would try to maximize this utility. On top of that, we also assume instead of knowing as mechanism, knowing the processing time of the jobs, we assume that these processing time are actually private to the machine. So only the agents know the processing time. And the mechanism needs to elicit the true value before they can make any reasonable decisions. So let's look at the naive approach that we were saying earlier. We wanted to allocate it to the cheapest machine, and we can pay the machine the processing time that they report. In this example, we would pay the first machine a payment of 1, which results in a utility of 0 for the first machine. However, this naive approach has some loopholes in it. In particular, the machine 1 has the alternative to report a processing time of 2. Now, the machine 1 will still get the job because 2 is still less than 3. However, the utility she gets from reporting a 2 instead of a 1 would be 1 instead of 0. So she can increase her utility by reporting a 2 instead of a 1. And in general, we would want to prevent this type of lying option for the agent by designing strategy-proof mechanisms. So a strategy-proof mechanism is a mechanism consists with an allocation rule and a payment rule such that no agent can benefit from misreporting, which is exactly the scenario. If agent 1 misreports to 2, she can increase her utility. And we don't want this type of behavior to exist in a strategy-proof mechanism. And for this specific setting, the long line of literature of mechanism design actually already provided us with a solution called the second price auction. So the second price auction says that you allocate the job to the cheapest machine, but instead of paying whatever they claim, we pay them the second cheapest processing time. And it's not hard to verify that the second price auction here is in fact truthful or strategy proof. So let's formally define the general setting of strategic scheduling problem. This problem was first considered by Nisa and Ronan in their famous algorithmic mechanism design paper that essentially started AMD, and it has been an active research area for the past 2 decades. The general setting consists of n unrelated machine and m jobs, and the machine I takes Pij to run job j. And I'd like to emphasize here again that in the strategic scheduling setting, these Pijs are private information. And the objective is for us to find an allocation X that minimizes the make span, where make span is the maximum sum of processing time of any machine. For this specific example, if we know all of the processing time, the minimum make span is achieved by assigning each of the job diagonally, and the minimum make span would be 1.1. So in a full information setting, if we know everything, there is a 2 approximation polytime algorithm, and it is still NP hard to approximate it within a factor of 1.5. So even if in the full information setting, we won't be able to solve it optimally in polytime. Now, in the strategic version of the problem, Nisa and Ronan considered the famous VCG mechanism on this problem. But VCG essentially is just running second price auction for each of the job individually. So for each of the job, we're gonna allocate it to the cheapest machine and pay them the second cheapest processing time. So if we run VCG on this specific instance, we will allocate all of the jobs onto the last machine. And this in turn would result in a processing time, in a make span of 5, where the optimal make span is 1.1. So we know that the second price auction or the VCG is not gonna be optimal. And in fact, this greedy approach could be as bad as n factor away from the optimal. And Nisa and Ronan in the same paper conjecture that not only does VCG needs to suffer this bound, they believe that no truthful mechanism can achieve an approximation better than n. And very recently, Christodoulou et al. Proved that no truthful mechanism can achieve approximation ratio better than 1 plus square root of n. So even if the conjecture is wrong, the best worst case guarantee that we can hope for is still pretty horrible. One thing we'd like to point out is that though, both the negative result and the conjecture heavily depends on the assumption that the mechanism has no clue about the private processing time, which given the amount of historical data we have on hand nowadays, and also the advanced machine learning techniques, this assumption is a bit unrealistic and also pessimistic. This motivated the study of the following problem, that given an accurate prediction, somewhat accurate prediction, had P about the private processing time P. So for each of the job machine pair, we have a prediction over the actual processing time. Can we design a mechanism that takes in both the prediction and the actual instance and achieve a much better performance without sacrificing too much of the worst case guarantees? So we're going to use the 2 metric that we introduced earlier in the algorithm design with prediction framework called consistency and robustness, where the robustness takes in the worst combination of prediction and the actual instance. Notice that the prediction and the actual instance doesn't need to be the same. So we allow the prediction to be arbitrarily wrong. And the worst, the performance of robustness needs to hold no matter what the combination is. And consistency, on the other hand, measures the worst case competitive ratio given a correct prediction. So notice here, we're assuming that the prediction and the actual instance is identical. Now, prior to our work, Xu and Lu in this year's paper considered the exact same setting, and then they proposed a mechanism with constant consistency and n-cubed robustness. In this work, we proposed a mechanism called scaled greedy and showed that the scaled greedy mechanism is strategy proof, 3 consistent, and 2n robust. And in fact, our bound is parameterized by gamma, where we achieve 2 plus gamma consistent and 1 plus 1 over gamma and robustness. So just to kind of like take another extra 10 seconds to interpret the result a little bit more, we're saying if the prediction provided to us is correct, we get no more than 3 times more than the optimal make span. And even if the prediction is completely wrong, we can still get a small constant away from VCG, which is the best known worst case guarantee out there. And due to the time constraint, I won't be able to go through the details of our mechanism. So for the rest of the talk, I will try to deliver the key concept of our design and hopefully provide some useful insights and intuition about algorithm or mechanism design with predictions in general. So to kind of like get the wheel going, let's focusing on the easy task first, which is guaranteeing a good consistency. Remember that to get good consistency, we just need to perform well when the instance is exactly the same as the predicted instance. Since we're given the predicted instance, we can pre-calculate the optimal make span allocation. For example, if we're given this specific predicted instance, we know that the optimal schedule would be to schedule the first job on the first machine and the second job on the second machine. So we know which job we should put on which machine. Basically, we have a destination for each of the job. So note that as we showed in the previous example, these optimal machine might not be the machine output by the greedy allocation. For example, for machine 2, the greedy would assign the machine 2 on the first, the greedy would assign the second job on the first machine instead of the second machine. One thing we can do though, is for each of the job, we can scale up the processing time of all of the other machines just enough so that the optimal machine would win even if we run greedy. So one thing we can do here is we can apply a scalar of k for the second job on the first machine. Now, the benefits of running this scaled greedy type of approach is that we essentially get strategy proofness for free. So as long as the scalars we apply is independent of the actual instance, we can always make the allocation rule strategy proof by pairing it with some payment scheme. So again, consistency only binds when the actual instance is exactly the same as the predicted instance. So consider the case where the actual instance is the same as the predicted instance. And we know that if we apply a scalar on the second job or with the first machine, running greedy would give us the optimal schedule that we want. So what we could do is take the actual instance, apply the scaling that we said earlier, and run the greedy on the scaled actual instance, which would give us the optimal schedule that we want, which is the optimal schedule of the actual instance. So this approach of pre-calculating the optimal schedule and scale up all of the processing time of all of the other machine give us the optimal consistency. But let's take a look at how does the scalars affect the robustness, because that's also one thing we also need to achieve. Now, remember that the robustness needs to hold, the performance guarantee we get for robustness needs to hold no matter what the actual instance is. And the actual instance could look completely different from the predicted instance. So consider instead the actual instance being as follow, where we mispredicted the processing time of the first machine for both of the job. So instead of having k and 1, the processing time of the first machine is actually 0 and 1 plus epsilon. And now, as we said earlier, the scalar we apply needs to be independent of the actual instance. And in order to achieve the good consistency, we need to apply this k-scalar. And if we apply the k-scalar on this actual instance, we're going to get a different scaled actual instance. And if we run the greedy on this specific instance, we're going to get the same allocation as we did before, which result in a make span of k. However, if you look at the actual instance, this specific one, the optimal schedule, the optimal thing to do would be to assign both of the job on the first machine instead. And the optimal make span in that case would be 1 plus epsilon. And now since our mechanism output is k, and then the optimal make span is 1 plus epsilon, and k could be arbitrarily large, we therefore showed that the scaled greedy version 1 has unbounded robustness, even though it has 1 consistency. And in fact, in our paper, we showed that not just the scaled greedy, any one consistent strategy proof mechanism must suffer this unbounded robustness. So in order to achieve any reasonable robustness, one inevitably needs to relax in terms of consistency. And if we kind of like take a step back and look at why we're suffering the unbounded robustness, it's probably due to the fact that we're scaling a lot in one of the machine job pairs. This essentially, we're blindly following the prediction to enforce one specific allocation. And once the prediction is wrong, we have no guarantee whatsoever. So this observation leads us to the scaled greedy version 2, where we're taking the initial version, but adding a cap on how much we can scale up the processing time. So the mechanism, again, given the prediction, would calculate the optimal schedule and try to make the optimal machine for each job the cheapest machine by scaling up all of the processing time of all of the other machines. However, if the scalar we need to apply is more than n, we simply apply a scalar of n instead. Now, intuitively, this version should give us a better robustness because we're limiting the bias we're imposing on the outcome. In other words, we're kind of messing with the instance a little bit less. However, since not all of the jobs are necessarily going to the optimal machine, because for some of them, we might not scale them enough, we're definitely going to lose in terms of consistency. Well, the good news is that we showed that the jobs that we assign suboptimally are actually negligible in terms of consistency. And in fact, even if all of such jobs ended up in the same machine, they contribute at most 1 extra optimal make span in terms of consistency. So in our warm-up session, we showed that the scaled greedy version 2 is too consistent with n-squared robustness. And we have an instance to show that the squared robustness is actually tight. So just to provide some like high-level intuition of how we get this n-squared robustness, this is a compounded fact of both VCG and the scalar, where in VCG has this myopic effect where we're supposed to assign the jobs diagonally, but we ended up putting all of them on the same machine. And each of the job on the same machine on top of the VCG also suffered from this scaled up effect of n. So that's how we get the n squared of robustness. So version 2 essentially provided us with a way to improve robustness without losing too much in terms of consistency. In the final version of the scaled greedy, we really exploit the idea and we try to bound the scalars more aggressively and carefully. In particular, scaled greedy essentially takes the first version, and instead of bounding the individual scalar at n, we bound the sum of the biggest scalar of each machine at n. And we also try to avoid scaling when the consistency constraint is not tied on some specific machines. And using these two nice properties, we showed that the scaled greedy version 3 has achieved 3 consistency and 2n robustness. And if you're interested in how we guarantee these two nice property and how these two nice property help us prove the bound that we're claiming, please check out our full version of the paper for details. So besides this, nice mechanism that achieves asymptotically the best of both worlds guarantee in terms of consistency and robustness, we also propose this error-tolerated scaled version of the mechanism that obtains good guarantee even if the prediction is not fully correct. So if we let eta, which is the maximum mispredicted ratio, to be the error of the prediction, given an error tolerance parameter hat eta, the error tolerated version of scaled greedy achieves an approximation of 3 eta square if eta is less than or equal to hat eta and hat eta square n otherwise. So what this result means is that you can predefine how much error you want to tolerate in your mechanism by like toning the mechanism a little bit differently. And if the actual error of the prediction is within the error tolerance level that you set, you get this 3 eta square approximation ratio, which is much better than the robustness bound that we're claiming earlier. And even if your error is above this error tolerance level you set, you still get bounded robustness. And in particular, if the error tolerance level you set is constant, and if your actual error is within this error tolerance, you still get constant performance. And even if your error is above this error tolerance, you still get linear robustness no matter what. So just to kind of like provide high-level consistency robustness trade-off at high level, for this specific problem, we know that to get good consistency, we essentially need those scalars to guide the jobs to the desired machine. However, to get good robustness, we need to avoid scaling as much as possible. And in general, for algorithm design with prediction or mechanism with design with prediction problems, to get good consistency, we inevitably need to introduce some sort of bias or favor for some specific outcome over some others. Whereas to get good robustness, we need to limit in terms of how much we're trusting the prediction and how much bias we want to impose on these outcomes. And designing a good mechanism that has nice trade-off between consistency and robustness is essentially finding the delicate balance in terms of how much bias you want to impose on the outcomes and if an outcome is like reasonable in terms of both of the objectives. So just to summarize the paper and also the talk, we revisit the strategy-proof machine scheduling problem with the learning augmented framework. And we achieved 3 consistency with 2n robustness with the scaled greedy allocation rule. And on top of that, we also have the error tolerance version of the mechanism that achieve good approximation ratio, even if your prediction is not completely correct. This result asymptotically matches the best consistency with the best known robustness. And finally, we'd like to take the time to motivate or to like advertise the learning augmented framework. Essentially, you can use the framework and revisit any mechanism or algorithm design question you like, as we believe this framework is really useful and hopefully would motivate us to design more practical mechanisms in the future. And that concludes my talk. Thanks.